Hello. This is meant to be a simple demonstration of how undaunting or how not so complicated it is to program or to write code in the LabVIEW programming language for those considering the Introduction to Robotics course. It is far simpler than you may think. This is the platform, LabVIEW. You will have access to it, of course, as UIS students. It'll be made available to you through the UIS web store, and we will also make available to you virtual machines that have this already installed and configured to use. When it starts, it takes a moment to start, you will see the interface. I'm using LabVIEW 2013, probably will have 2015 or 2016 available to you. The interface doesn't change from generation to generation, it's just there's some more libraries available every now and then. So this is what you start with, and we will start with a blank project. It might be easier to start with a blank VI actually. I'm not going to build an entire project, we're going to start with a blank VI, just work on a simple VI. The VI means virtual instrument, and you're presented with a number of windows, and I'll talk about each of them in turn. This is the circuit diagram window. This is where you do the programming. This is the interface, which is what the user will see of your program and interact with. You can simply resize the windows to meet your needs. A couple of function palettes available to you. So for the programming side, you have VI libraries. These are libraries already written bits of code that you simply wire up together, and we'll see that in a moment. So this is your function palette. This is where most of the work happens. This here is a context help. For each item on the palette, you get brief relevant information about the item, and if you want more information, there's always the detailed help, which you click on that and it brings up a web page like document, and all these documents are hosted on your own machine, so you don't have to wait for internet connection or anything, so they will exist in your machine. On the outside, this is the user panel, or this is the virtual instrument that the user will see, and this is the panel onto which you'll design your interface, and these are the controls that you can put on your interface. For this brief demonstration, I'm going to build a simple 5-function calculator, and as a demonstration of how quick it is and how easy it is to put it together. And once I have the calculator running, I might actually use its output and input as controls for a simulator, let's say a signal analysis simulator. So I'll start by designing the interface. I want a left operand and a right operand, so I go to the numeric palette and pick a numeric input. I need 2 of these, and numeric output, I need 1 of these. Then I will need the operator, and the simplest way to create an operator is to get the text input combo box, which is just a drop-down list. Once you have this is the base of the interface. This is left operand, right operand, operator, and results. And if you right-click on this and pick properties, you get a configuration panel for this drop-down list. Change this name to operation. I'm happy with the size, and I'm happy with how it works. I want the items in it, so I'm going to insert a whole bunch of items. So I want 5 operation, addition. You just hit the enter key and it drops to the next operation. And I want subtraction. The next one will be multiplication. You can of course use abbreviation, but I will use the full name, division. Raised to the power, and remainder. For those of you who have done some computer programming before, remainder is a modulo operation if you haven't done computer programming before, but you're aware of at least some of the math around, it's a floor and remainder function, and I want the remainder out of that. So if you have 10 and 3, or 10 over 3 remainder of, so you divide 10 by 3, you get 3 whole 3's, and you have 1 remainder. So that's the result will be a 1. You can insert a tip strip information, select the operation needed. It's always good to have a default item in here, but I'll do the default program in the programming side to show you how this is done. So this is all built. Now calculators don't do just one operation, they run basically forever until you tell them to not run. So I'm going to move all these guys in here and then encase all of this in a loop. In this case I'm going to use a while loop controlled by a switch. Grab this tool and draw the loop. So here's a while loop, this is the stop condition. I'm going to right click on this and create a control, and now I have a switch in here. You can see you can redesign, redraw the switch. I just want to move it in the middle of the screen so we can see it. So here's my stop button. Move these apart a bit to make more space. Now the easiest way to do this is to draw a state machine controlled by this operation here, and for every time the user chooses an item from here, it changes the state machine from one state to the next. So I'm going to build a state machine using a case structure. And I'm going to change the labels in the case to the names that I have put in this drop box, in this combo box. So my first name is addition. And then I right click in here and say add case after. The next one was subtraction. It's important to get this spelling identical to what you inserted in the documentation of this, or in the properties version of this box. I hope I don't make any typos. You just add another case. After that I have multiplication. Followed by division. Followed by raised to power. Followed by remainder. And I'm going to make my false case is the default case. So now I have my 5 operations: addition, subtraction, multiplication, division, raise to power, remainder, and default. Default means catch all. If you haven't allowed for some operation that exists here but don't exist here, the default will just catch it and throw something out. So now I need to wire up all these cases. We say wire up because really the VI and the programming side of the VI reflects a circuit board, so the circuit boards are wired together, and this is what we're going to do. This is how we write the code here. So having 2 numbers, numeric is not very helpful, so I'm going to change the name of these guys and call this operand, left operand. Right operand. You can leave them as numeric 1, numeric 2 if you want to, but it looks better that way. First is addition, so I'm going to come here and go to the mathematics side of things. Here we go, and pick this library, the math library, numeric math library, and there's an addition sign. And you can see here on the context help also it tells you that this is it computes the sum of inputs, and there is an X and there is a Y, and they're wired to the side, and X plus Y comes out from the other side. So here I'm going to create a wire. There's the X. Incidentally, we have a tool palette here. This is the actual tool you use, the tools you use. I've got the auto select tool selected, which is, this means it'll select the most appropriate tool when I bring it close to a terminal. As you can see, it turns into a wiring coil, and this is exactly what I want, so I'll just keep using that. You can specifically say, or tell it to use only a connect wire tool, but I don't find that to be extremely as helpful as the auto select tool. So these are my inputs, and the result of the operation goes into numeric 3, which I'm going to rename as result. That's it for addition. Subtraction, the same story. Minus. You see, connecting the operands into the case statement gave me terminals within the case statement, so I didn't need to rerun the wire from the outside again. I'll just grab them from the terminals. Here we go. That's it for multiplication, division. We'll get the division. 2. And as you can see, while I'm doing all this work, the arrow is broken, which means there are things incomplete, or there are some errors that basically are missing connections, and all these connections going nowhere here. They're causing the errors. But once I connect them all, they all disappear. So raised to the power, this is going to be interesting. You can do it programmatically, so you can have a little loop doing the raise to the power, or you can do you can find the correct tool, which is in here under Express, in Express Math, and I have an exponential function, and just a matter of picking out the right one. Power of 2, power of X, power of 10. So this is the most appropriate one, power of X. I'm going to grab this, put it in here. So we want the left operand to the power of the right operand, and you can look here. So the left of, connect this guy here, the left operand, raised to the power of the right operand. And there is my outcome. Just goes there. And the remainder, so I need the floor and remainder tool. I'll just go up here. This is my floor and remainder tool. And the R refers to the remainder, so this is x minus y times the floor will give you the inputs. So it's like 10 over 3 and the remainder is 1. So I want the R terminal. This all done. I still have a broken wire because my default case has no outputs. So I'm going to pick positive infinity as the output in my default case. And here we go. I now have a working calculator. And we can test this. 12 here, 23 here. Nothing happened. Why? Because this is already, these variables have already been read the moment I hit the start button. So I need to pass these variables around from one iteration of the loop to the other. I will stop that and deal with this right now. So like with every programming task you've done, you need to initialize your variables. So I'm going to initialize these variables to 0. So I have constants here, 2 0 constants. I'm going to connect these just to the edge of my loop, like so. So give me these tunnels, and now I'm going to right click on the tunnels and say change these tunnels to shift registers. And shift registers are basically variable value feedback. Shift registers, whatever goes in here at the next iteration of the loop, it's available in here, and I'll just initialize. So this will only be read once at the time I hit the play button, and from there on they just read what's in this register. Obviously I don't want them to fight with these values. I want to disconnect them from here, disconnect these guys from here, and connect these guys to the shift registers. So when I hit the start button, the first time the operation will be carried out using these inputs here, which are my initial start values. But from there on, every subsequent iteration, it'll read what's in these left and right operands. And I can reinitialize this to default, reinitialize values to default, so everything goes back to zeros. So first run, or first iteration, is going to read 0 and 0 as the inputs. I'm going to do whatever operation I tell it to do in here. Let's run it. So here is 0, 0 input, and I'm going to do a subtraction. I should get a 0. Now I can give it new values in here, and the moment I hit enter, the operation is carried out. That was a subtraction. Let's make that into addition. There is your 25 into remainder. That should be 12. 12 divided by 13 is 0, remaining 12, raised to the power. So it appears to be working correctly. And hit the button to stop it. Stopping. I notice that this window is a bit small, so I'm going to enlarge it one more time. And I'm going to raise to the power. Yes, I got enough space in here, so this is the maximum value being able to be held in this variable. In this case, it is it's narrower than integer, so this is the maximum integer plus something to the power of 13. So you can play with the types and get it to display the real numbers. That being the case, I've done all of this. I'm reasonably happy with this calculator, and I would like to have some fun, or at least make it do some cool things. Not very meaningful, but they're going to be cool anyway. They'll look cool. So I would go to signal processing and find a signal generator, a waveform generator. Under these, and find a basic function generator, or you can pick any one of these. And of course, later on, when we're doing some signal analysis, some real signal analysis, we might specify something useful as opposed to something that just looks cool. So I'll place that in here, and from the output on the context help, I can see there is that signal output. That's probably give us the most interesting visual. So I'm going to right click on this guy and say create an indicator. It gives me a numeric indicator. It's not a big problem. I want a graphical, so I'm going to right click on it and say replace it with a waveform chart. So I'm going to get a graph of the wave. Now, of course, waves will have frequency, amplitude, and phase. And I'll connect my results to the amplitude terminal. And let's connect this guy here, right up around to the phase. Okay, let's see what it does. Looks produce some kind of waveform. Of course, a static waveform it is not, because if I change that value to some other, it changes because based on the results. But again, I can do some more interesting things with it. I'll stop that here. Go to back to the numeric, and let's pick a ramp control, or just a knob if you like. You can use this to ramp up or down the signal going in there, the amplitude of the signal. Here's the ramp. There's a numeric value coming out of that. I'm going to use it as a multiplier. To the result. Simply click on the wire and delete a section of it that breaks it, and then you reconnect that. Now if you have little bits of wire that are disconnected, like this guy here, Control B will simply get rid of them. And let's have a look at that. Now, given that the ramp is set to 0, whatever value is up here is multiplied by 0. We have a flat line here, but this will change as soon as you give it some value. Just change the waveform shape. You see the X and Y scales at the side, they're auto size, but you can actually fix them at some value. You just stop the auto sizing on the X and the Y. Its values have been stopped. And now you can simply wrap this up. If the top value is too low, you can increase that, say to 25. And if you want it symmetric, you make the bottom value also 25 on the opposite side. And here is your waveform, you can see. Okay, so this really concludes the demonstration. It's just, my aim was to show you that it is not a programming language to be afraid of. It's not daunting at all. It's very simple. Everything makes sense, and it's a safe language. You can't make a mistake. It will not run if it is not correct, and if it's not correct, where your bracket error is will tell you exactly where the syntactical error is. If you want to make the wiring diagram look more complex, simply go to the edit tool and say clean up the diagram. I like to clean up my diagrams once I've finished building them, so they become compact, and I can display 4 or 5 of them at the same time and compare the programming or see where things are. And these are all the different cases. I hope this helped you make a decision to take the leap and consider Introduction to Robotics as a course you wish to take part of. Certainly a very good programming language to learn for those who are considering a career in computer science. Most industrial processes use some kind of control and automation language. This is the most widely used in the world, not just in the USA, but in the world. I came from Australia, and this was a language we were using everywhere. That's it. Have a great day. Thank you.